Hello everyone and welcome back to another data structures with Python lecture. Today we're going to continue working on binary trees. In the last lecture we saw how to program a very simple tree with Python, and today we're going to continue that. Now what we're going to have today is an example of a simple binary tree. Okay, so in the last lecture we saw an example of a tree. In this lecture, we're going to see a simple binary tree, and in the next lecture, we're going to see the full binary search tree. Now, the reason behind that is that the delete operation with binary trees is not easy. It's a little bit complex, so we're not going to go into it today. What you're going to see is how to add, how to print, and how to find nodes in a binary search tree. Now, what you want to understand once we start is the difference between doubly linked lists and binary trees, because in reality they are really similar to each other. Now we had the names. We had the name previous and next. We call them in the binary trees, we're going to call them left and right, but they are the same. They are pointers that point to another node. We had the data, which we're going to call value, but it is again the same. We're going to use numbers and integers in here. We had a pointer called head, which pointed towards the first node in a linked list. Now we're going to have the root, which points towards the root of a binary tree. Each one of the nodes in a doubly linked list pointed towards no more than two nodes. So it pointed towards none, not a single node, one node, or two nodes. So we didn't have any case where a doubly linked list node would point towards three or more. It was always two or less. Same exact thing with binary trees. By the definition of a binary tree, each node in it can point towards 1, 0, 1, or 2 nodes. It cannot point towards 3 or more. So as you can see in here, they are really similar. We just changed the names in here, but how they work is the same. The only real difference between the two is traversal. So with linked lists, our traversal was straight, which means you start at the head, you jump to the next, all the way until the end. Now with binary trees, we don't have a line. It's not a linear process. We have multiple levels or multiple layers in our tree. So you have a tree that starts in here at the first level or the root, then the second level, third, fourth, fifth, and so on and so forth. So how can you traverse that tree? And we use either in order, pre-order, or post-order. The thing that you're going to see with binary trees is that they rely more on recursion, on calling the same function over and over again by itself, which means when you, for instance, when we're going to program how to print, you're going to see that we're going to do a method for printing, and the method is going to call itself in a fashion, whether it's in order, pre-order, or post-order, so that we can access all of the information inside of our tree, or all the values rather inside of our own tree. Now let's start by drawing a simple tree, and for that I'm going to go with my friend Visual over here. And the thing that I want to do, let's take an example. Okay, I'm going to use a circle because a lot of the time trees are used with circles, no problem. So let's go with let's say that we do number 10. Okay, do this. So start with number 10. This is going to be our root. Then this is just an example of the top of my head. So let's add let's copy and paste in here. It's going to be much faster. So this is, if we add the number 7, it's going to be on the left. Again, just to reiterate in here, binary trees are trees that have no more than 2 nodes. So something like this is going to be a binary tree. Binary search trees will always have a value that is lower to the left, a value that is higher to the right. So if I had the following values, let's say I have 7, 10, 13. I started with 10, so it's the root. Then I have 7. If it is lower than 10, then it should be added to the left. If it's higher than 10, then it should be added to the right. And as you can see in here, 7 is to the left. Then we took the number 13. And the same thing happened. Okay, are you lower or higher than the root? It's higher than 10, so it goes to the right. And so on and so forth. So I'm going to add some numbers randomly. If we add the number, let's say 0. So 0 is less than 10. It's less than 7, so it's to the left of it. So it's going to be in here. Oh, actually, sorry. To this. So this is going to be 0. If we add the number, how much? 100. Okay, so 100 is more than 10. It's more than 13. So it's going to be here to the right. This is 100. If we add the number 9, say, so 9 is less than 10, so it goes to the left, but it's more than 7, so it goes to the right. So number 9 is going to be right in here. And let's say that we finally add the number 90. So 90 is more than 10, right, more than 13, right, less than 10, left. So 90 is going to be here. So as you can see, I'm now going to do the connectors. So normally, each one of our nodes is going to link to only 1, 2, or 0. So either no nodes, for instance, 90, 9, and 0, all of them are not pointing towards anything. Other nodes are pointing towards them, but they are not pointing towards anything. We call them leaves. So you can point towards nothing. You can point towards 1. As you can see, number 100 is pointing towards 1. Number 13 is pointing towards 1. Or you can point towards a maximum of 2. So you can see number 7 pointing towards 2. Number 10 is pointing towards 2. This is a binary tree. And since the lower numbers are to the left, higher numbers are to the right, this is a binary search tree. Okay? So this is what we're going to work with today. To make it simple throughout the upcoming lectures, I want to give a few tips in advance. One of them is that we are going to use something that is a little bit new to you, which is encapsulation. So encapsulation, you have already studied it with the OOP lectures. The main idea behind it is that we are going to hide code inside of other codes so that the computer would see just one function, which means I can do the function for add, which I'm actually going to do. So if I define add in here, or insert, as we have worked with before, what's going to happen is that I'm going to do a simple check. Just check in here, especially for empty, because we're going to check for empty a lot. We're going to do a separate function, separate method for it. So I'm going to do the check, and if the check passes, so the if statement, if it is true, something will happen. If it's false, which means the else for it, we're going to do real insert. We're going to actually call the real function that does the insert. Why? Because we're going to work with recursion a lot. And if I do the checking, especially for empty, it's going to be a hassle. It's going to be difficult to do inside of one method. So normally what happens is we would have two methods. One of them is for doing something. The other one is going to be the real method that does it. So this first method is going to check for my condition. If it is working, then it's going to call the real one. How this is called encapsulation is because this is hidden, almost hidden. The call for the method is hidden inside of this main function, let's call it. So if this function doesn't call it, it's never going to be called. All of our program is going to call this method, not this one. And only if the check is passed, then we're going to call the real one. This is one type of encapsulation. This is going to give you more security later on. I'm not going to take too much of your time. I'm going to stop this video right now, and in the next video we're going to start actually programming our simple binary search tree without the delete. The delete is going to be for the next lecture in the next week. Thank you so much, and I'm going to see you in the next video.